Good afternoon to everyone. I welcome all of you to the 72 lecture in the lecture series in nonlinear dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It is my pleasure to introduce today's speaker, Professor Arkady Pikovsky from University of Potsdam, Germany. I don't need to introduce Professor Pikovsky's name to major part of this group. Everyone who works in the nonlinear dynamics, chaos theory, or statistical physics in one way or other came across his name in the research papers. Anyhow, in view of the students, I would like to tell his research topics in a very brief manner. Professor Pikovsky works on several frontier areas in nonlinear dynamics. To name a few, I spell out, he works on synchronization, data analysis, nonlinearity and disorder, studying the effects of noise in dynamical systems, space-time chaos, dynamics between order and chaos, and a statistical theory of chaos. In each one of the above topics, he carries out research on multifaceted angles. I encourage the students to visit his homepage and learn the topics in more detail in which he is actively working on. Professor Pikovsky has written 4 books, among which the most popular one, in my view, is Synchronization, a universal concept in nonlinear science, published by Cambridge University Press. Any new entrant in synchronization theory will never miss to see his book or to read his book. Professor Pikovsky has acquired a very high H index, which I noticed that 73 in the Google Scholar. His works have been cited more than 37 times worldwide. Today, he is going to talk about dynamics of oscillator populations, exact finite-dimensional reduction and beyond. With this short introduction, now I request Professor Pikovsky to deliver his lecture. Over to you, Professor.
Yeah, thank you very much, Sinti-Lieven, and I am very much excited to be able to present our results and in some more generic, maybe, context to this audience. So the topic of my talk is dynamics of oscillator populations, and it includes several collaborations with different persons, so I will give references to the literature at the end. So it's the motivation for this study and in general for this topic of many oscillator populations. So it comes from the many experimental setups or observational setups where one has a system of many oscillators which are somehow coupled and demonstrate different phenomena from which, say, synchronization is probably mostly spectacular. So here on this first introductory slide, I show several such systems. So one can put many metronomes, which are self-sustained oscillator, on a common platform and observe their behavior, or rather unintentionally, so pedestrian on a bridge can demonstrate such a collective dynamics being interacting with modes of oscillation of this bridge. So this is a famous case when such transition to synchronization happened at the opening of the Millennium Bridge in London. Or one can supply some clocks through genetic manipulations into cells. And in this experiment done by a group of around Jeff Hastie and Lev Zimring at the University of San Diego, so they had several millions of cells. Each of them had a clock inside, and these clocks were interacting and synchronized by some chemical agents in the surrounding. So it's indeed a very large population, and more or less you can say that all these cells feel the same surrounding. There are many other examples from physics, so coupled lasers, or from life sciences like flashing fireflies. In all these cases, one deals with many coupled oscillators. And so in this talk, I will speak not about some complex networks, but more or less about globally coupled oscillators. But let us start with some basic things with derivation of equations for these oscillators. So the first basic step is a so-called phase reduction. So the idea of the phase reduction is the following, that one has an oscillator which may be described by some system of nonlinear differential equations. And the assumption is that there exists a stable limit cycle, so which describes periodic motion of such oscillator. There could be a metronome or a pedestrian which works regularly, some other cases. So formally it is a periodic solution, isolated and stable, which has some period, and heat is relation of period to frequency. And so the idea is to introduce the phase. And the phase is essentially the variable which measures which part of the limit cycle we are now passing. So one can not only on the limit cycle itself, but in the whole basin of attraction, introduce such a variable. I'll not go maybe into more details. And always one can find renormalize such variable in such a way that it changes by 2 pi by one cycle and grows uniformly in time. So it describes like phase in elementary physics, so the part of the cycle, and it grows. Now, the next step is to look on what happens if there is some force acting on such oscillator. This force can come just as an external force or force from other oscillator. At the moment doesn't matter, but the assumption is that this force is small. So in this case, so one can perform this so-called phase reduction, just writing an equation for the phase. You see, so you take this definition of the phase, take time derivative, and you see that there is some additional term. And in this additional term, in the first order, in epsilon, you can assume that the variable lives on the limit cycle. And on the limit cycle, it is a function of the phase only. And so this is a closed equation for the phase. This is a very remarkable reduction because from any high-dimensional system, just in the case of limit cycle, you can reduce the dynamics to that of one variable which lives on a circle. And this phase equation, so it is a basic starting point to perform a further analysis. So it's you can simplify this, and in some cases you can write this phase equation in a form where there is some part which is coming from the external force, and there is some part which is coming from this derivative, which is called phase sensitivity function. So this is a closed equation which describes what happens to limit cycle oscillator under external forcing. Now, if you look for two oscillators, then each is described by its own phase, and the procedure which I outlined above of the phase reduction delivers such a system of two coupled equations. So for one oscillator, which probably has natural frequency omega-1, for the second oscillator, and there are two coupling terms which in the proportional to the small parameter, which describe how these phases interact. Now, it's typically one makes still one more term, one more step to average over fast motion. So you see, so frequency can be considered as large parameter compared to the interaction. And so the phases deviate from their normal rotation rather in a slow manner. And one can make this averaging if one goes to the slow phases. So when subtracts, so this fast rotation, so that the new phase will be slow and only slow terms remain on the right-hand sides of this equation. So slow terms essentially mean so that we have only differences of the phases. And with this averaging, we get from this still not so complex equations to even simple equations where only phase differences appear. So these are equations already averaged. Averaged coupling comes from this general coupling through this integral. And so this is the final point of simplification. So simply it cannot be, so this just one function of phase difference determines what happens to these two oscillators. And typically in many cases, so it's generically this function is 2 pi periodic, but in many cases one just takes a sine function and investigates the system in this limit. Okay, now if we have many oscillators, so already the previous approach says so that we still can perform such a phase reduction in the fully similar way. And the only thing is so that now we have many elements. So we put here index k to identify oscillators. And they're interacting through mean fields. So mean fields could be just some observables of these variables. And this is rather generic formulation. But in the terms of phase reduction, we say that all oscillators live on their limit cycles. So we describe them by phases. And so these mean fields should be functions of the phases. And all such functions, which should be 2 pi periodic, can be described by so-called order parameters. You see, it is just you take these phases, and this is resembles some kind of Fourier modes of the distribution of the phases. Yeah. So you have here additional index m, so which can change from say 0 or 1 to infinity. So you have in fact many order parameters which all describe potential mean fields which are coming here. Yeah? And the phase reduction here reduces the phase dynamics to just rotation plus interaction of the given phase with the mean fields. Yeah. So this is a generic equation which corresponds to such type of coupling where only some mean fields are coming as potential forces. Now, if you average this, still in the next step, So that means that only slow variations on the right-hand side should remain in this term, and the slow variations are those which are phase shift invariant. So it means that it corresponds to our previous consideration that there should be only phase differences. And so that terms like this, or this, or this, or this, so can appear on the right-hand side. So you see, so the sum of indices of these mean fields taking with the proper sign, because here it is complex conjugate, should correspond to the number which comes in this exponent. So all these terms are possible, but in the simplest examples of the mean field coupled oscillators, one considered just very simple terms. So the most famous in the field is the Kuramoto model, which will be soon 50 years old, where the coupling term just contains only one term proportional to the first order parameter. So if you write this term as a sum, then you come to the following equivalent formulation of the Kuramoto model, as an oscillator is coupled to all other oscillators with the same coupling strengths, and the coupling of each pair is proportional to the sinus of the phase differences. So it is a direct generalization of the system of two coupled oscillators to the system of many or all-to-all coupled oscillators. And so there are other models, and the different physical systems give different types of equations. And below, I will also use the following model of the which comes from a series of overdamped Josephson junctions. So I'll not go into details of this physical system. It's just right equations, so where you see that the phase, Josephson phase, is governed by this term, and this term comes from the load, and this sum of sine functions can be written as an imaginary part of the first order parameter. So you again have an equations where on the right-hand side there are order parameters and terms which are proportional to, say, sine, cosine of the phase. So now I turn to a more generic formulation, and I will not speak first about this particular models like Kuramoto models and Josephson junction, but because my talk will be more about methods than on physical results, so it will be how you can deal with the generic equations, I include all possible couplings and external forcings just in these two arbitrary functions of time. So one, this function of time, so it is real, and h is a complex function. So, and they can depend on the order parameters, or they can contain explicit functions of time, whatever. So our goal at the moment is to look on this system, which can be interpreted as an ensemble of oscillators which are driven by two common forces. One common force is real and another common force is complex. But they are common to all oscillators. Therefore, there is no index k here in omega and h, and the only index is here. And here it is only term with the first harmonics. So there is no terms with second harmonics. I will discuss such terms later because the main theory can be written only for this case. So these equations could be written for 1, 2, 3, many oscillators, but for the theoretic methods, we want to go to the so-called thermodynamic limit. Thermodynamic limit is that of infinite population. So it is infinitely many oscillators, and in this case, so we describe them with a distribution density of the phases. So this is a function, a real function of phases and probably time dependent. And this ensemble, very much similar like one does in statistical physics and kinetic equations, obeys a kinetic, or in this case, Liouville equation of the conservation of this probability. So this equation is just a first order conservation of probability where the flux is proportional to density multiplied with the velocity, and for velocity you should put here this term. Okay, so this is the equation for the density, and the equations which we need also for the order parameters, because they potentially could come here. So they are just go from sum to integrals. And one can see so that these integrals are nothing else as Fourier integrals. So the order parameters are in fact the Fourier modes of this distribution. Of course, so due to normalization, zero Fourier mode is 1, but all other modes are non-trivial, and they non-trivially depend on this. Now we have a partial differential equation, we have Fourier components, and this one equation in a standard way can be written as an infinite system of now ordinary differential equations for these Fourier modes. It's just a standard procedure how you deal with partial differential equations. And here it is simplified because it is not equation on a real line, but equation for the 2π periodic function of phi. So it is phi changes from 0 to 2π, and this everything is periodic. Therefore, there is discrete Fourier modes, and the system of equations is for these Fourier modes. By the way, so if there are any questions, so please don't hesitate to interrupt me, and I will also try to follow this signs from the screen. So if there are signs about questions, so I will stop and ask. But at the moment, so we just formulated the problem of identical globally coupled, not globally coupled, but identically driven oscillators in the thermodynamic limit. Okay, now in many cases, so one can say that there are some noise in the system. So let us try to incorporate also noise terms. So noise we consider as independent on each oscillator. So for noise, we take here this index k. If there are some common noises, they could be included in these functions omega and h. But independent noises have index k. Now the equation is for conservation of probability. Should be something like Fokker-Planck equation. And in the case of Gaussian and white noise, with intensity sigma. The standard Fokker-Planck equation looks like this. So there is a so-called diffusion term for the probability due to this noise, and the system of infinite system of equation, you still use the same definition for the Fourier modes, is now looks like this. There is an additional term depending on the noise intensity. But so on the circle, also other noises are possible, and we will focus below on so-called Cauchy noise. It is white noise, but not with Gaussian distribution, but with Cauchy distribution. You can say, okay, Cauchy is a bad distribution because it has fat tails, but here we consider everything on a circle. So it's anyhow, the variables are not on real line where it is dangerous to have large deviations, but on a circle there are no large deviations, everything from 0 to 2 pi. And therefore, Cauchy noise appears not to be much, how to say, worse than the Gaussian noise, but it has definite advantages. For Cauchy noise, we cannot write a standard Fokker-Planck equation, but we have to write a fractional Fokker-Planck equation. So essentially, this fractional derivative is well defined in the Fourier space, where instead of having a term n square, so if you multiply this n with n, it will be n square for Gaussian, it is simply proportional to the n in the Fourier representation. So for Cauchy noise, you have a slightly different system of equations. So you see difference is in this noise term. Here it is n, and here there is no factor because we divide here by n. Now let us look at another type of non-identity, which you can call disorder. So we say that oscillators have slightly different frequencies. So these are constants, so psi k are constants, which are have some distribution. And this means so that oscillators have different natural frequencies. And one can take also Cauchy distribution or Lorentzian distribution of these frequencies. And it's now we cannot write one Liouville equation, but we have to insert this parameter psi in this equation. And so it will be a distribution of phases for a given frequency. And so it will be not just one Liouville equation, but a set of them for different values of this frequency psi. And the mean fields are defined through this integral where you additionally average over this distribution of frequencies. Now, why it is still tractable? Because so there is one trick in this field, which first was done by Ott and Antonsen in 2008. And this trick is quite often used also in other contexts in plasma physics and in optics, where Lorentzian distribution is somehow used for. So the idea is to assume analyticity of this function as a function of psi in the continuation of psi to the upper half complex half plane. So psi is a real variable, but you continue this function to the complex values of psi. And then you realize so that if this function is analytic, this integral can be easily calculated because this distribution has just one pole in the upper half plane. And through the residual theorem, this integral can be reduced to just one value, xi equal to imaginary I. And doing this, you reduce your system just to, again, to system of equations for this order parameters, which is written here. So let me summarize. So what we achieved so far, we considered a system of oscillators, in this case, not identical, but with maybe noise terms and with some distribution of frequencies. But nevertheless, it was possible to reduce all the systems to the infinite set of equations for the order parameters. So, and you can realize so that the case of distribution of natural frequencies of Cauchy white noise, the equation essentially coincides. It's the same equation. So it doesn't matter whether you have Cauchy noise or Cauchy disorder. The equations are the same. Here there is additional assumption of analyticity. For Gaussian noise, it is a different equation because here it is factor n. So now,
Professor Pikovsky, can I interrupt for a moment? This system of equations, the system of equations we have reduced seem to be linear, set of linear equations.
Yeah, you see, so it is looks like linear, but nonlinearity is hidden there because this omega and h can depend on z.
Oh.
You see, omega is not a constant. Okay, here I don't write this, but omega is a function of time and h is a function of time, and they potentially can depend on z. So I will give an example so that you will see how it works. So h and omega depend on z, and this brings nonlinearity in this.
Okay, thank you.
But for the derivation, it doesn't matter much. Okay, thank you for your question. Yes. Okay.
I have one question then.
Yes.
So omega is not the intrinsic frequency usually which is assumed in the Kuramoto oscillators, correct?
Okay, so you see, let me go back to this. You see, here in the Kuramoto oscillators, omega is a natural frequency because it is constant.
Mm-hmm.
But you see, if you look on Josephson junctions, there is additive term proportional to the order parameter.
Yes.
So in this sense, so you cannot interpret omega as a natural frequency. It contains some frequency.
I see. So right now,
something which comes from the coupling.
Mm-hmm. Okay.
So it is a most generic situation is when both omega and everything could depend on order parameters.
Yes. Okay. Thank you.
Okay. So these are these equations, and you see it is an infinite system. All equations is infinite system. You can work with it. You put on computer. Of course, you cannot solve infinite system, but you can try to maybe truncate it at some point if these order parameters decay, and still you can have consider, I don't know, 400,000 of these equations and treat them, and this will probably work. But our ideas, not only ours, but general ideas, if you can reduce this infinite system to something finite. And there are indeed, I will here give two references. So it is infinite dimensional system, but there are existed in literature two remarkable finite dimensional reductions. So the first was done by Watanabe and Strogatz already almost, I don't know, 30 years ago. And they have shown that without noise, so this term gamma describes noise or disorder. So without disorder or without noise, the system for any initial conditions can be reduced to 3 real variables plus a constant function. You see, so this was a very remarkable result, and it says you see, so it means so that this constant function means so that there are infinitely many integrals of motion. And so you can say, so it is a to large extent integrable system because the dynamics lies on some 3-dimensional manifold. Yeah, it is exact result. Now, the next step was done by Ott and Antonsen in 2008, and they have found now in the case with noise a particular invariant manifold, which, okay, we will discuss below, it's attractive, which reduces the dynamics to 2 real variables. So in this manifold, I will already say it here, but I will discuss a little bit more details below. So all order parameters are related to the first one by this relation. So higher order parameters are just the first order parameters in power n. And if you substitute this here, you will see so that this is invariant. So if your initial conditions are here, you will go on this, it will continue like this. And if they are not, okay, you don't know at the moment, but so there are arguments that you will approach to this case. Now, what I will present below is our recent result that for any initial conditions, with noise, with gamma not equal to 0, the dynamics of this system can be reduced to 6 real variables and a constant function. So if there is a gamma non-zero, we can show that there is attraction to Ott-Antonsen manifold within this exact 6-dimensional dynamics. And for gamma equal 0, we will show that this our equations reduces to the Watanabe and Strogatz equations. So this is what we think somehow making a bridge between these two approaches and more or less so gives what happens in this system for any initial conditions. Yeah. So now here I have to apologize. So in fact, I cannot show here any derivation because it is 2 pages of different transformations and different, I would say, introduction of generating functions and manipulation with them. Looking on series, so even in our publication, we delivered many, how to say, calculations to appendices. You should maybe refer to go to these calculations. I don't think for a lecture it is appropriate to give these complex calculations. And already you see it's a relatively complex formula which is presented here, says so that these calculations, okay, they are more or less straightforward, but not so trivial that you can explain them in a lecture. So I just give here the results and discuss them from different sides. So these 3 complex equations are dynamical equations of the system. You see, so they contain the same variables, omega, gamma, h. Omega, h could be any functions of time. Gamma is a constant. These are all variables are complex. So you have a system of 3 complex equations, but okay, so there are 6 real variables. And another things which you need always is to represent your order parameters through these variables, 3 variables. And you see, so this is the formula, and it, contains some sums, so binomial coefficients. And there is one function of m, we call it here, which is a constant. So it will be defined by initial conditions, but it doesn't depend on time. You defined it from initial conditions and it remains constant. And here there are derivatives of this function. You see, so it is general formula. It's just to impress you so that it works. And but say for the first order parameter, which we'll need in all our cases, there is all the sums, so they come from the following expression, which contains q, y, and s. So m is a function of s is this third variable, y is this second variable, and like this. Now you can, I immediately will say that this system already contains Ott-Antonsen case if you put just y equal to 0. You see, if y equal to 0, this equation remains, so it is always fulfilled. And from this formula, you see this is y here. So all these complex terms disappear, and you see so that z order parameters are just a complex number in power n. So this is exactly the Ott-Antonsen case, and you remain only with one equation. But so the idea is, but this is just one manifold. It is not generic for initial conditions. So I again repeat this here in this slide. So if y is 0, you just have one equation for this complex Q, and you have the following relation to the order parameters. And the distribution function of the phases, also, of course, depends only on this value Q, and it is a so-called wrapped Cauchy distribution. You can write it in the following way. And this includes, this distribution ranges from the uniform one. If Q is 0, then you have just uniform distribution of the phases. And a fully synchronous distribution will be delta function. And in this case, absolute value of Q is 1. And its argument gives this where the phases are concentrated. And now it was also your question, so where nonlinearity is coming. You see, for the Kuramoto model, H is proportional to the first order parameter. So the coupling is through the mean field, and it is proportional here. And you see this equation is nonlinear. Yeah, so it is a fully nonlinear equation which describes in the Ott-Antonsen approximate on the Ott-Antonsen manifold the dynamics of the Kuramoto model. For the array of Josephson junctions, you see, so here omega depends on Q, H is constant, and the equation looks like this. Yeah, so it is again equation, second order equation, exactly describes this array on the Ott-Antonsen manifold. So it is included in this theory. Now, I promised you, so you see, you write equations, but you have to choose initial conditions. So here I have rewritten these equations. There are, in fact, could be different choices, so one choice, which is always possible, is the following. You set Qs to 0, y to 1, and in this case, this function is just defined as using the initial order parameters. So in this equation, you have some initial conditions, initial order parameters, and through them you define this constant function. It will be constant in time. Or equivalently, you have initial distribution of your phases, you calculate this integral, and this will be this function. So you can put any initial distribution, calculate it. In many cases, you can do this analytically, say for delta function, for whatever, if this integral gives you some analytic function. So, for example, if you have initial conditions where only several order parameters are non-zero and others are zero, so it is a finite Fourier series, then this function will be a polynomial. Yeah, it is clear here. You don't have infinite sum, but some finite sum. Yeah, so these are initial conditions. Now, I promised you also to argue so that we can have Ott-Antonsen and Watanabe Strogatz in some limits. So if you can a little bit manipulate with these equations, you can define some new variable, which, okay, combination of y and q, and then derivative of this variable will be like this. And because q is less than 1, so you see it is always negative. And it means so that this variable decays. And you can say that, define the following expression for this variable y. And remember, case y goes to 0 corresponds to Ott-Antonsen manifold. And this shows that this is indeed in the framework of this theory. So this manifold is indeed attracting. Now, but this doesn't work if gamma is 0. In this case, y is a constant. You see, if gamma is 0, this is a constant. One can show that this, if you, according to our initial conditions, this y and this another variable s, they just have absolute value 1 and therefore can be represented in such form. And this, for theta, you get one equation which looks like this. And together with the equation of q, it is exactly this set of Watanabe-Strogatz equations. Remember, there were 3 equations in the Watanabe-Strogatz theory, and this is one complex equation for q and one real equation for theta. So these are these limiting cases. Now I give some numerical illustrations. First, it's just shown that how this variable y indeed approaches Ott-Antonsen manifold. Here there is a dynamics of this Josephson junction model. It's in the equations, it is chaotic if gamma is 0, and this is red curve here. It shows chaotic dynamics of this ensemble, but on the Ott-Antonsen manifold, the dynamics is regular. And you see, introducing small values of gamma, you see convergence to this manifold, and this convergence for variable y just is here compared to our estimate of how this variable should decay according to the theory. Okay, so it is indeed lies below these upper limits. The next illustration is how good is description for finite ensembles. Okay, the theory is in the thermodynamic limit. We cannot derive anything for finite systems, but as usual, we expect that for large number of units, it will work. And here there are order parameters evolution for the Josephson junction model for finite ensemble and for in the thermodynamic limit with our exact equations are overlapped, and you can hardly see the difference. So this shows that indeed, say 10,000 are enough to this thermodynamic limit to be valid. Now, so you can ask the following question. We have shown that Ott-Antonsen manifold is attracting, and so why, for which purposes one could use these exact equations, because they describe only transients. And here we show a situation where these transients might be important. You see, for asymptotic states, it is enough to consider Ott-Antonsen equations. So if you have attractors, they can lie only on this Ott-Antonsen manifold. But suppose we make some perturbation, which not necessarily rely on this manifold, but we manipulate our oscillators, and then want to look where they will come, to one attractor or to other. It means so that we have to define the basin of attractions. And it should be defined outside of the Ott-Antonsen manifold, because we cannot generally expect that the perturbation will be exactly on this manifold. So these ideas of resetting, by the way, you can find also in the recent paper by Shamik Gupta and Mrinal Sarkar, published in Chaos. And so here there is this experiment with resetting, which is large. So we consider a situation where there is a bistability between synchronous and asynchronous state. And we start in synchronous state, make a large perturbation, say with uniform distribution of phases, and maybe only first harmonics, and maybe with a delta function. So we take some oscillators and give them another distribution, and then let evolve and find basins of attraction. And this cannot be done within Ott-Antonsen theory, because these perturbations, so they bring system outside. But with our equations, we can easily do this just following the 6-dimensional system. So I want to conclude this part. So we have shown a low dimensional reduction for a population of oscillators, but there are several restrictions. So coupling is via the first harmonics only. You have Cauchy noise or Cauchy distribution for natural frequency, but not Gaussian noise, and there is thermodynamic limit. Now, if I don't know how much time I can shortly show some couple of other cases where I consider multi-harmonic coupling and Gaussian white noise if there is some 10-15 minutes left.
Yes.
Yeah, okay.
Yeah.
So I will only shortly say what is difference. Now, let us look of what is called multi-harmonic coupling. You remember, so we started with this equation where only first harmonic coupling was present. Now, it is you can derive some theory which is below. It is for any number of harmonics, but I will just, for brevity, consider two harmonics. You have coupling in the first harmonics, and you have coupling in the second harmonics. And you have a Cauchy noise here. So this is now the model. And if you write equation for the order parameters, it is again an infinite system, but you remember previously it was only these two terms, with so-called nearest neighbor coupling in this Fourier space, but here it is next to neighbor coupling. And if you have more harmonics, the more modes are coupled here to the left and to the right. Yeah, it's just this harmonics gives you corresponding neighbor in the coupling. So, and here Ott-Antonsen doesn't work at all, Now, what can still be done? Unfortunately, not so much, but there is one observation. So we cannot derive a closed equation for some modes or global variables, but we can look at stationary solutions because they are, in many cases, they are important solutions. So we assume that time dependence on these autoparameters is just so they rotate uniformly in time with corresponding frequencies. And then, so for these time-independent variables, Z, you reduce the system to such a, how to say, lattice system, which doesn't have any time dependence. And remarkably, there is no this factor n because it disappears on the left-hand side. You see, so this is a homogeneous system, and it can be solved by a power ansatz, this system. And generic solution or general solution is just a sum of these powers. And these complex numbers are roots of the characteristic equation. You substitute this here, just one power, you get characteristic equation, you find roots, you look on the roots which are less than 1, and this is your generic equation, and this constant satisfy, so this the such represented. You see, so it is you see, so the solution here, it's infinite system, but it can be described by two complex numbers, lambda 1 and lambda 2, and this lambda 1 and lambda 2 should be solutions of this characteristic equation. It's just how to say, lattice system. It's interesting that such two, of course, so if there is a just Ott-Antonsen case or first harmonic coupling, it is just one such term, and where it is a Ott-Antonsen case. Now, it is interesting that what a distribution describes this, it is a superposition of so-called Carter-Jones distributions, which have been introduced recently, or a product of wrapped Cauchy distributions. So it is still finite dimensional because there are only two complex numbers, but we have a find this equation, these numbers depend on the H, and H also contain autoparameters, so these lambdas should be found somehow self-consistently. Here, I give some example of biharmonic coupling. It's maybe not so important. It's just to illustrate so that now the distribution you see with biharmonic coupling could be two hump. So it is not just a simple distribution like for one harmonic coupling, but it is superposition of these two. And interestingly, so this system has steady states, but also time periodic solutions. And if the states are steady, so this our approach fully works. So error is 0, but for time-dependent solutions, so unfortunately, our approach doesn't work. So it is only works for stationary states. So I conclude this part. So here the coupling is multiharmonic. It's a definite generalization, but works for stationary solution only, and only for Cauchy noise or Cauchy distribution for natural frequencies, and also in the thermodynamic limit. Yeah, so it is maybe less so striking result. But nevertheless, multiharmonic coupling is an interesting case. Okay, now you see, so we said for Gaussian white noise, we cannot do anything previously. Now let us look at this case carefully. Gaussian white noise means so that there is an additional term here. So we have, again, infinite system of equations. If sigma vanishes, then the Ott-Antonsen manifold is attracting. And so the idea is to look what can we do if sigma is small. So then we can assume that maybe we are close to the Ott-Antonsen manifold, and this will allow for some kind of perturbation theory. And so it appears so that there is a nice way to construct this perturbation theory if one doesn't look on these autoparameters or circular moments, but to so-called circular cumulants. You know that in theory of stochastic processes, one introduces cumulants to describe distributions which are close to a Gaussian one. So Gaussian distribution has two non-zero cumulants and all others are zero. But if you have something close to Gaussian, then you have quantities like skewness and kurtosis, which are defined through the third and fourth cumulants, which could be small, and you then can describe situations close to the Gaussian. It happens that here, for the distributions on the circle, you also can define cumulants, and the case, they are now complex numbers because moments themselves are complex, and it happens that on the Ott-Antonsen manifold, all higher cumulants vanish. So this is a nice starting point for the perturbation theory, because you can now assume that higher cumulants are small and describe situations close to Ott-Antonsen manifold. And so indeed, in the case of small additional terms, you can argue that higher cumulants are small, they are proportional to powers of this small parameter, and you can truncate the system of cumulant equations at some term. For example, you can take only the first cumulant, which will be the main order parameter, and the second cumulant, and about third cumulant, there are different choices of how you can set it zero, or you can make maybe some better choices. And so the result is now it's approximate four-dimensional system. You see it a system of differential equations for now the main cumulant, main order parameter, and the second cumulant. It is approximate, but it is low dimensional and works only if there is a small parameter sigma, small noise. And you can compare how this system works compared to just Ott-Antonsen approximation and say one can get only Gaussian approximation. So we considered a noisy Kuramoto model. We say Ott-Antonsen doesn't work exactly. And you look on the errors of the order parameters from different approaches. So if you just make Ott-Antonsen ansatz, so your error will be this blue. It is small, but nevertheless, somehow. If you make Gaussian ansatz, it is red. So you see, in some cases, it is even better than Ott-Antonsen, but still, in many cases, it gives large error. But in our approaches of two cumulant approaches, so you see they always lie below this and provide, in this case of small noise especially, very essential improvement, several orders of magnitude. If noise is larger, then this improvement is not so large as to be expected because our approach is perturbative. Okay, so concluding to this part, it was about Gaussian white noise, so which is not destroys Ott-Antonsen manifold. and it is based on cumulants of which are circular cumulants. So the approach is not exact, and coupling is in the first harmonic only in the thermodynamic limit, but okay, case of noise can be included here. So here I want to finish. So there are essentially, it was about 3 topics. So the first and main topic was about this exact reduction to 3 complex equation. And this is work done with my postdoc Rob Chesnik and published this year. This case of multi-harmonic coupling was done with Ralph Tonius in our group. And this circular cumulant-based perturbation theory was done with our colleagues in Perm around Denis Golgodobin, was published several years ago. So thank you for your attention. We'll be happy to respond to questions.
Oh, thank you, Professor. Thank you. The forum is open for questions, doubts, clarifications. Students.
Looks not immediate questions. So anyhow, so if anybody will have questions in the future, so please write me. I will be happy to respond.
Are there any questions from the students? Oh, we are not getting any questions, Professor.
Okay, no, but it's so. Thank you anyhow for invitation, and was happy to present our findings. And yeah, so wish you a very successful continuation of this lecture series.
Thank you, Professor. Thank you. So I would like to conclude the session by thanking Professor Pikovsky for accepting our invitation and giving a wonderful talk on for a general talk. Okay. Thank you, Professor. Thank you very much.